Welcome back again. This is going to be episode number 30 of Learning by Doing MPI, and it's going to be part number 2 of virtual topologies in MPI. So we're going to continue from where we left off last time. So we were talking about this MPI car create, which was a Cartesian constructor. We sort of talked about the arguments that it gets and a little bit about its behavior. But we haven't basically seen the examples about that. And we have read the standard up until here. We haven't talked about this MPI dims create. But let's take a look at the code itself, MPI card create, the C. Okay, these things up until here, we're not going to talk about them because we have already seen this pattern in hundreds of examples. So these are the arguments that we need. So we need dimensions. So let me go back here. We need dimensions. Sorry, that's ndims, number of dimensions. In this case, it's 3. And we need dimensions. It's right here. That is the number of MPI processes in every dimension that you have. So in this case, we have 0, 0, 0. So right now, we haven't occupied this with any value. I put a comment here. We're going to see the behavior of this later. So we have periods, and that is whether we have periodic condition for every dimension or direction that we have. And this is we have 0 for every direction. And we have coordinates, again, since we have a 3-dimensional Cartesian grid, then our coordinates are going to have 3 values for x, y, and z, you can imagine. And then the reorder is also 0. It means that there's no reordering is allowed. So that's the Cartesian communicator with type of MPI com. And we use MPI dims create, and you can see it right here. We already mentioned in the first part that the dims create is sort of a helper function to basically select a balanced distribution of MPI processes per coordinate direction. Depending on the number of MPI processes in the group to be balanced, and optional constraints that can be specified by the user. It takes number of nodes, that's sort of the MPI processes. Then it takes the number of dimensions. In our case, it's basically 3 dimensions. And we passed in dims, which we have initialized it with 0 in every direction. So 0 in this case means that this sort of function is allowed to associate different values for every direction, direction 0, direction 1, direction 2. And MPI dims create does it in the non-increasing order. So the first sort of direction is going to have the largest value. The second is going to have the second value, and the third is going to have the third largest value. And it does it in a way that you're going to have a balanced distribution. So for example, in our case, we are using 12 processes. So you know that, for example, we have 4 times 3 or 2 times 2 times 3 if you're going to have a 3-dimensional Cartesian grid. So this means that the first element is going to be 3. It's always non-increasing in what MPI dims create does. So it's going to be 3, 2, and 2. This is how dims create does this. So we're going to see that in action in a second. So we have this MPI car create. We pass in those proper arguments. And the rest of the stuff, I'm not going to comment on them because we have like inquiries, which we haven't talked about those functions. But basically, after creation of that, we try to print something from different coordinates and different processes in that Cartesian topology. And then we are trying to basically use some of those inquiry functions to print some more information about our Cartesian topology. Yeah, so I'm not going to basically go through the rest of this sort of example, but I kind of scroll down slowly so that you can pause this video and see the code quite easily. So you don't think that there's any magic happening. So I think you got all the code, and then in the end, you need to basically take care of the garbage collection or the resources that you have allocated. You need to free them once you're done with them, and then you call MPI finalize, of course. So let us just run this MPI car create, let's see, and MPI run minus NP 12 processes we said we need. And you see that proc0 has coordinates, is also part of MPI com world and has the coordinates 0, 0, 0. It's a three-dimensional grid. Process 1 is 0, 0, 1. And as you can see, the largest sort of index for the first dimension is 2, which is 0, 1, 2. That is 3. And then the largest index in the second dimension is 1, as you can see in all of these processes. So this means we have 0 and 1, 2 dimensions. And again, the largest sort of number for the third dimension or the third component is basically, again, 1, which we have possible values of 0 and 1, again, 2. So as I said, MPI DIMS creates 3 by 2 by 2. So it's non-increasing and it's as balanced as possible. So, for example, it could create also 12 times 1 times 1. It could also create, I don't know, 6 times 2 times 1, but they are not as sort of balanced as 3, 2, and 2. I think you already got the idea. What do we mean by being more balanced? And then these are those sort of inquiry functions that the cart communicator, the communicator that we basically populated, is a Cartesian communicator indeed. And cart communicator has 3 dimensions indeed, because our coordinates have 3 values. And then cart com contains the following number of procs in every dimension, respectively. It has 3, 2, 2. That is what we said, basically judging by the index values for every dimension. And then so these are the periodicity information in every direction or in every dimension. We have 0, 0, 0, so this means we don't have any periodic condition in there. And then root process has the following coordinates. So of course process 0, you see it also here, process 0 has the coordinates of 0, 0, 0. And then proc 5 has the following coordinates. You can see it also here. Where is proc 5? Proc 5 is right here. It's 1, 0, 1, and it's also reflected 1, 0, 1. This is, again, one of those inquiry functions that you can use to print sort of the coordinate of your process, of your basically the process that you want to choose. Rank of proc 5 is also 5. This is another sort of function. These might sound dubious, but once we talk about those inquiry functions, everything is going to make sense to you. Then proc 5 knows root process has the following coordinates. So this also shows that since these sort of functions are local, this means that proc 5 has already information about the coordinates of the root process. So that's the example that we had, but let's go further down. This is MPI DIMS create. We already talked about this, that it's going to find a balance of those multiplication with a divisibility algorithm. And it's going to basically find the closest or the more balanced scenario. And then negative input values of DIMS I is going to be erroneous. And, you know, and again, an error is going to happen if there are not the multiples. Those multiplications are not going to add up. Again, we already mentioned that it's going to be in non-increasing order, 3, 2, and 2. And then we said MPI DIMS create is local. So these are examples. For example, DIMS before call, 0 and 0. And so that is, let me show you. So this is the DIMS that we passed. We initialized it with 0 and 0. Our example was 3-dimensional. This example is 2-dimensional. So imagine that we have a 2-dimensional scenario for our Cartesian grid, and the initial values that we supplied for DIMS array is basically 0 and 0. And then we use MPI DIMS create with these values, 6, 2, and we pass in this DIMS, which is 0 and 0. So you want to have 6 number of processes, and then you want to have 2 dimensions. So this is what MPI DIMS create is going to basically dump out for you. That is 3 times 2. It's going to be 6. You have 7 processes. You want to have 2 dimensions, and your initial values are 0 and 0, it's going to dump out 7 and 1, because 7 times 1 is going to be 7. You're going to have 6 processes, 3 dimensions, and you have another restriction, and the restriction is that the second value is going to be 3. So if this one was 0, 0, and 0, then it's going to return 3, 2, and 1. But since the initial value is 3 here for the second argument or for the second dimension, then what this MPI dims create is going to do is going to figure out the rest of those multiplications. That is going to be 2 and 1. So the multiplication of all of these is going to be 6. And if you have 7 here for 3 dimensions, if this thing was 0, 0, 0, then this call was not erroneous. It could return 7, 1, and 1 in non-increasing order. But since the second argument or second dimension is going to have 3 processes, it's not possible because 7 is not divisible by 3. So that is why we have erroneous call. I think this table basically gives you all the information you need about this MPI dims create. Okay, let's take a look at the second example, which was MPI card create V1, and let's see what the difference is. So here we have to use, instead of 12 processes, we have to use 7 processes. And this is the case that if you have, in this case, 2 times 3, we are not going to use, notice that we are not going to use MPI dims create in this case. We have already mentioned that what kind of dimensions or what number of processes we need in every dimension. So we have 3 dimensions. In dimension 0, we're going to have 2 processes. In dimension 1, we're going to have 3 MPI processes. On dimension 2, we're going to have 1 MPI process. So periodicity, again, it's not going to be periodic. And coordinates, again, is going to remain in 3. We have no reordering, but notice that 2 times 3 times 1 is going to be 6, but we said we're going to use 7 processes. So this means that 6 processes are going to participate in the Cartesian grid, the virtual topology, but 1 process is going to be left alone, right? So we call this MPI card create. Every process has access to this function call or to this topology constructor call with the proper values or proper arguments. And then we say if the card com is not MPI com null, because we said for that process that is left out or left alone, it's going to return with MPI com null. So we put an isolate if statement here. If the card communicator is not MPI com null, then we ask for the coordinates and we print something to the console. And in this case, we know that process rank number 6 or the last process is going to be alone. So that is why we basically check that process 6. And indeed, the value for card communicator is going to be MPI com null. And it's going to print that, hey, I'm alone. And for freeing, you need to also mention that freeing only needs to happen on the valid processes, because process 6 has MPI com null and it's not proper, or you're going to have errors if you try to call MPI com free with process rank 6. Okay, so let's try to run this. MPI CC MPI. Whoops, what am I doing? Card create V1, and let's run it with minus NP7, we said. And if you do that, then you see that process 6 is going to say, hey, I'm left alone, and other processes, again, this has coordinates 0, 0, 0, process 1 has coordinates 0, 1, and 0. And notice that the first sort of dimension or direction has the maximum index of 1, so this means 2 processes. The second direction has the maximum index of 2, so this means 0, 1, 2, 3 processes. And the third direction has only 0, and that is only 1 process. And that is exactly equal to these 2, 3, and 1 a number of processes for every direction that we had. So going back to MPI card create, the original version, you see that here I put a comment that you need to try value of 3 with the middle element. So with the second sort of direction, let's put 3 here. So what's going to happen? what's going to happen is that we have 12 processes, and MPI dims create tried to in the first example, we saw that it was trying to create 3, 2, 2. So that is the pattern that it creates for the Cartesian grid. But if you put the second argument to be 3 and the other ones with 0, so it's going to take 3 as a value that it has to be there for the second direction. So we are going to have 3 MPI processes in the second direction, and then it's going to assign these and this and this in non-increasing order. So let's take a look at that. MPI CC MPI cart create.seam and MPI run. Of course, we have to try with 12 processes, not with 7. And then you can see that the largest index for the first direction is 1. So we have 2 processes. The largest index for the second dimension is 2. We have 3. And you can see also this pattern here. We don't need to see these indices. So we have 2, 3, and 2. So this is how it basically figured it out. So, if I go down here to show you that it's working in sort of non-increasing order, I put this one as 2, and let's see what is going to be returned. You see that it starts with 3. So again, it always works in non-increasing order. So if you put the middle one, if you limit the middle dimension to have 2 processes, 2 MPI processes, the first one is going to be 3, and the last one is going to be 2. Okay, so this was the example, and we haven't commented about these inquiry functions, but we're going to see them later in this chapter. Okay, the second constructor is a graph constructor. We have an example for that, MPI graph create. So vim MPI graph create. So before discussing that, let's take a look at the arguments. Again, it needs n nodes. It's the number of processes, number of nodes that you have. Then you have index. Index has a little bit of strange meaning. So maybe we're going to see the meaning of index in a second. Let's not talk about index right now. Edges is basically as obvious as it is. So edges is sort of those edges that we're going to have communication along them. We have reorder, that is ranks may be reordered. If it's true and it's going to be false, it's not going to be reordered. It's a logical one. Again, it's a integer. Edges is an array. Index is an array. What is the size of those arrays? It's not the number of processes. We're going to see it in a second when we see the example. And then graph is the sort of communicator that comes out. Again, this returns a handle to communicator to which graph topology information is attached. If reorder is false, then you don't. Then the ranks of those MPI processes are going to be the same as in the old communicator. If the reorder is true, then the same thing happens. It has the same meaning. If the number of nodes in the graph n nodes is smaller than the size, then MPI com null is going to be returned, similar to Cartesian. In analogy to MPI cart create and also MPI com split. If the graph is empty, so the number of nodes is 0, then MPI com null is returned to all MPI processes. The call is erroneous if it specifies a graph that is larger than the group size of the input communicator. Then the 3 parameters and nodes index and edges define the graph structure. So in order to define that graph structure, you need these 3 parameters: n nodes, which is the number of processes that you have in this index or those indices. It's sort of a cumulative number of neighbors that you have. That's the real meaning of index. And edges is basically a list of all neighbors you're going to have. So we're going to talk about that. Imagine this example 8.2 that we have 4 MPI processes, 0, 1, 2, 3, and process 0 has neighbors 1 and 3. Process 1 and process 3 are the neighbors of process 0. Process 1 has only one neighbor, and that is process 0. Process 2 has only one neighbor, and that is process 3. Process 3 has 2 neighbors, and that is process 0 and 2. And you can kind of notice that it has a symmetry, right? Because process 0 is in contact with 1 and 3, and you see process 1 is in contact with process 0, and process 3, which is the neighbor of process 0, is also in contact with process 0. And you see that process 2 is in contact with process 3, and process 3 is also in contact with process 2. But we're going to see later that there is no necessity that you're going to have symmetry in your sort of virtual topology, right? Okay, so that's the number of nodes. It's going to be 4. The index is going to be, the index is going to be 2, 3, 4, 6. What's the meaning of that? So you see that process 0 has 2 neighbors. So that is why we have the first element to be 2. Process 1 has 1 neighbor, and that is process 0. So 2 plus 1 is going to be 3. Process 2 has 1 neighbor, and that is process 3. 3 plus 1 is 4. And process 3 has 2 neighbors. 4 plus 2 is going to be 6. So that is cumulative number of neighbors. Edges, on the other hand, shows the exact neighbors that we have. 1, 3, 0, 3, 0, 2. 1, 3, 0, 3, 0, 2. So you see that it's sort of a linearization, or it's sort of a flattening happening here, that edges is basically a flat version of all those neighbors that you have. And also notice this, it's very interesting. Number of index elements. So how many index elements you're going to have, that is equal to the number of nodes or the number of processes you have. So you see that I have 4 processes. My index has the size of 4. We have 4 elements here. How many elements you're going to have in edges, that is equal to the last number in the index array, which is 6. So you see that we have 6 elements here. Why the last number? Because it's the cumulative number of neighbors. So the last element shows basically how many total numbers of neighbors you're going to have in your sort of virtual graph topology. So that's basically the meaning of it. And we're going to see this beautifully in this example. So these things are repetitive. We have seen it. And you see we're working with 4 processes this time. Our index is 4. 2, 3, 4, 6. 2, 3, 4, 6 is exactly a replication of that example 8.2 right here. And then edges is going to be 1, 3, 0, 3, 0, 2. 1, 3, 0, 0, 3, 0, 2. And I also put some comments here. We're going to talk about those comments in a second. Reorder is 0. Again, reordering is not allowed. And then we have the graph communicator, and then we call those that constructor with those proper naming or the proper arguments. And then the rest of these stuff, we print some stuff, and then we put a barrier here to make sure that we are printing stuff in order. And then we use some inquiries. We haven't talked about them. I'm going to scroll down like slowly so that you can see the whole code and see that there's nothing sort of special, or there's no secrets in these codes. And finally, you need to basically do some freeing in the end. So MPI-CC, MPI graph, create, run it, not with 12 processes, but with 4. And you can see that, let me clear the screen and do it again. So you see that process 0 has 2 neighbors. Those are processes 1 and 3. Process 1 has 0. Process 2 has 3, right here as the neighbor. Process 3 has the neighbor 0 and 2, right here. It basically dumps out the number of neighbors you have, and it dumps out the actual values of those processes. And then it says GraphCom has 4 nodes or 4 processes and 6 edges. We already know that. And we know that that sort of cumulative index array, it's 2, 3, 4, 6. That's the index. And we know that it has also the following edges, 1, 3, 0, 3, and 0, 2, which is exactly as this one. So a very beautiful example, a replication of the example in MPI standard. Oh, so nice. So we're going to continue in the next episode. Yeah, I wanted to also talk about these variations, but probably we're going to exceed the time. I'm going to continue in the next episode. Yeah, I'll see you in the next one.